across the orbit of Earth? Well, we can sort of tell pretty easily whether an asteroid is an Apollo asteroid or not by looking at its eccentricity. That's a big part of what's going on when you look at the orbit of an asteroid, because most of them have centimeter axes that are, again, around 2.8 to 3 astronomical units. So if their centimeter axes are all pretty close to each other, then the perihelion distance at the top there really just depends on the eccentricity, because that little a there is a centimeter axis. That's about 3 astronomical units. The eccentricity, you take 1 minus the eccentricity, multiply by the centimeter axis, that's the distance of closest approach to the sun. So if we're talking about an Apollo asteroid, we're talking about a perihelion distance less than 1.0167 astronomical units. That looks like sort of an odd number, because we usually think of the Earth as having an orbital distance from the sun of 1 astronomical unit, right? So why would the definition of the Apollo asteroid be that its perihelion distance is less than this funny number here, 1.0167? Not 1, but this number. Why is that? They want to stand up and give a brief statement? Somebody use the mic or something? Explain? No? It's just too simple. Yeah, you're right. It's just too obvious. Like, that's what you want comparison. So like making such an obvious thing. Well, it's because Earth's orbit isn't perfectly circular. Even Earth's orbit has a slight eccentricity. Okay? So when we're talking about an Apollo asteroid, we're actually talking about an asteroid whose closest approach, perihelion distance, is less than Earth's aphelion distance, which is the farthest that the Earth gets from the sun. Okay? You can cross Earth's orbit if the perihelion distance of the asteroid is less than the aphelion distance of Earth. And that's where that number 1.0167 astronomical units comes from. That's the aphelion distance for Earth's orbit. Okay, so what this basically turns out to give us is a kind of a range of values, because we do have some centimeter axis values that are as small as 1.6 for asteroids. They're not all out at 3. There is a range there from about 1.6 out to 3.5. So basically, the asteroids that are most likely to cross Earth's orbit and be Apollo asteroids are the ones with the least centimeter axis in the group, which is like 1.6. So we throw that into the formula up there. And then we have to have eccentricities greater than about 0.4. And then those asteroids will cross Earth's orbit, at least the aphelion distance. All right, now let me just show you the latest compendium. This still works. Yeah. All right, now there's a lot going on here. You probably, I'll have to email this link because you are going to need to know all these numbers. Final, so you might want to. There's a lot of good memory techniques out there, like the tutorials and stuff. You can use things like, well, I don't want to digress from it. I have a really good story about that. I don't have time. We need a larger lecture. Oh, I've been waiting to use that all semester. That's again like Jaws, the alligators, remember? You need a larger boat, and you need a larger lecture. About 3 months. Now let's see. Okay, so we have some columns that are kind of easy to read, like A. Centimeter axis right here, you can see numbers that look like, 1.8 down to, larger numbers, 2.3. Okay, so remember, this list is Apollo asteroids, so we're going to tend to be looking at objects that have smaller centimeter axes, because that's going to tend to make them be closer to the sun. The eccentricity, the eccentricity E over there, some of these have really large eccentricities, very large eccentricities. So for example, the very first one on the list actually has a Q over there on the left. That's its closest approach to the sun. That's really less than 1 astronomical unit, right? That first asteroid on the list has such an eccentric orbit, 0.961, that E column, that it actually could even strike Mercury. It gets so close to the sun at perihelion, it actually can even strike Venus or Mercury. And if we go down, that Q value you see in this column right here, I'm indicating, that Q value is basically the perihelion distance, and all these numbers are less than 1. So that's the key number, that Q, which is the closest approach. You see we're getting closer and closer to 1. We're up to 0.7 now. Let's see if we really go down the list here. Yeah, you see the numbers are all less than 1 until we basically hit 1 right here. So these are the perihelion distances. So there's thousands of these objects known. And the perihelion distance is the number which basically means it's an Apollo asteroid, because that's less than that distance we're talking about. So again, I didn't realize there were so many thousands of here, so probably a good thing to print this out and study this during Thanksgiving. Well, the Apollos are clearly the most dangerous for life on Earth because a lot of them are pretty large, and a collision with an object a few kilometers across would cause an explosion on the order of, well, 1,001 megaton nuclear bombs. I mean, not a good thing, definitely not a good thing. Complete devastation over 100 kilometers in diameter, and a lot of damage out farther than that. Fortunately, as I mentioned earlier in the semester, the rate at which large rocks are hitting things in the solar system these days is very low. There's lots of small material out there. There's lots of dust. We see shooting stars every night if we go out on a dark night in an area where there aren't too many towns nearby. And those shooting stars are tiny little microscopic dust particles, not a threat of any kind, right? So most of those objects that are striking Earth are really, really small, and there's only a relatively small number of large objects. All right, so the first Apollo asteroids were discovered actually not really that long ago, 1918, by Max Wolf. And by the way, the first Apollo asteroid discovered in 1918 by Max Wolf was not any of those large 4 asteroids we talked about. It's not Juno or Vesta or Icarus or Pollux, because those are actually not Apollo asteroids. So these are much smaller objects. But we know about thousands of them, and there could be hundreds of thousands of them, or even millions that are large enough to do some significant types of damage. All right, so asteroid impacts historically during the modern human era of life on Earth, there haven't really been very many large impacts of this kind. The largest known impact was all the way back in 1918, and by the way, that was even before Max even discovered the first Apollo asteroid. It was 10 years earlier, in 1908, the Tunguska event happened in Siberia. Basically, it was equivalent to a 15 megaton explosion. So this was an object hundreds of meters across, probably. Could possibly have been a comet. The reason I say that is because we've never found a solid mass in the ground in the epicenter of where the impact occurred. You would expect to find a massive iron body or something like that if it was a dense meteorite or asteroid. So it could have actually been a comet. But apparently the explosion actually occurred above the ground, and we do see some stony fragments, but that's not conclusive about whether it was actually a comet or an asteroid. Lots of nastiness happened. A few people were thought to have died, but it's Siberia after all. We didn't really know too much about who was there at the time. The Club Med cruise had been canceled due to bad weather, so at least we didn't have to worry about that. But you can see that what you find is trees that have been toppled in such a way that they pretty much point away from the explosion center, so that it was possible to actually find that center point. And the scale here, by the way, the scale of this event is around 50 kilometers. So again, this is similar to that distance we were talking about before, 50 to 100 kilometers for multi-megaton type of event. There have been plenty of smaller incidents, like explosions that were detected over the Pacific. They're actually detected a few times a year. And the way that we detect these explosions typically is by looking at pressure sensors. There's lots and lots of pressure sensors that are actually out there looking for nuclear explosions and things like that. But they can detect sudden pressure events which create shock waves in the atmosphere. And that's how a lot of these events are discovered, especially the ones that are impacts over the Pacific Ocean, because we don't have a continent out there, so there's not really people out there looking at things like this. Occasionally really bizarre things happen, like in 1972, a large object was kind of skipped off the atmosphere over Wyoming, and was almost like a skipped stone. It didn't actually penetrate the atmosphere, But it was seen by tourists out there, and they're awful lucky that it didn't come down on them. That's a big object. Would have caused a very large explosion. And then lots of people know about the meteor crater in Arizona, which actually is relatively kind of a recent phenomenon, about 20,000 years ago. This was an iron asteroid, relatively uncommon, and it was actually found, and they're sort of mining that. And then, of course, we have our 10-kilometer size object which struck Earth around 65 million years ago, which again is a type of impact that we don't expect to occur very often at all. Because, again, we don't really have enough of these large objects flying around. This is an artist's conception of the impact that caused extinction of the dinosaurs. You can see the nice big wave. It's a surfer stream come through. You can see this very large wave extending up multi-kilometers into the atmosphere. This would be good for the GoPro, the GoPro camera. You can mount it on your surfboard. It would have really been spectacular. And this is another artist's conception of this very large, massive rock, striking Earth. And this is kind of a romantic shot of some pterodactyls about a millisecond before they get incinerated by the wave of radiation coming off those things. Okay, that's